The Big Bang, you know the story. 13.8 billion years ago, there was nothing. Then, bang, a massive explosion. Matter flew outward in all directions. The universe expanded, cooled, stars formed, galaxies formed. Eventually, here we are. Simple, clean, dramatic, and almost completely wrong. There was no bang, there was no explosion. There was no center from which matter flew outward. There was no moment where something came from nothing in the way you are picturing it. The name Big Bang, coined sarcastically by astronomer Fred Hoyle, who thought the idea was ridiculous, is possibly the most misleading label in the history of science. And here is the thing that makes Feynman's perspective on this so extraordinary. Feynman spent years insisting that physics must be described honestly, that using vivid but inaccurate language to make science feel accessible is not kindness, it is a disservice. Because once the wrong picture is in your head, it is genuinely difficult to replace it with the right one. Today, we replace the wrong picture, not with something simpler, with something far more extraordinary. The real story of how the universe began is stranger, more beautiful, and more mind-bending than any explosion. Let us tell it properly. G'day, and welcome back to Curious Physics AU, the channel where we take the most famous ideas in science and ask, but is that actually right? I am Abdullah, and today we are tackling cosmology, the science of the origin, structure, and fate of the universe itself. We are going to cover what the Big Bang actually is, not the cartoon version, and what the evidence actually tells us. We are going to talk about the expanding universe, the cosmic microwave background, inflation, and the quantum origin of space-time. And along the way, we are going to ask the question Feynman would insist on. What do we actually know? What is solid evidence? And where does honest uncertainty begin? Because in cosmology, more than almost any other field of physics, the line between established science and speculative theory is critically important, and popular science blurs that line constantly. Today, we draw it clearly. Let us go. Let us start by demolishing the explosion picture completely, because every misconception about cosmology flows from this one wrong image. An explosion happens at a point in space. Matter flies outward from that point in all directions. If you were watching from outside, you would see a center, a place where it started. The Big Bang is categorically not this. The Big Bang is not an explosion in space. It is an expansion of space. There is no center. There is no edge. There is no point from which everything flew outward. Because at the moment of the Big Bang, there was no pre-existing space for things to fly outward into. Space itself, along with time, began at the Big Bang. Here is the analogy most physics teachers use. Imagine the surface of a balloon being inflated. Draw dots on the surface. As the balloon expands, every dot moves away from every other dot. No dot is at the center. No dot is special. The expansion is uniform everywhere. That is a better picture than an explosion, but it is still imperfect. Because in reality, there is no higher dimensional space the universe is expanding into. The universe is not the surface of a balloon expanding into a room. It is the balloon, and the balloon is everything that exists. The expansion is intrinsic. The fabric of space itself is stretching. And as it stretches, the distances between galaxies increase. So what does the Big Bang actually mean? It means approximately 13.8 billion years ago, the observable universe was compressed into an extraordinarily hot, extraordinarily dense state. All the matter and energy we can observe today was concentrated into a region smaller than an atom. Space was not infinitely small at that moment. We do not know its actual size. But the portion of space we can currently observe was compressed to subatomic scales. From that state, space expanded rapidly. The matter and energy in it cooled and diluted as the volume increased. Particles formed, atoms formed, stars formed, galaxies formed, not an explosion outward from a point, an expansion everywhere simultaneously. That is the Big Bang, the real one. Now, here is where Feynman would plant his flag, because he always insisted, in science the evidence is everything. Theory without evidence is storytelling. So what is the actual evidence for the Big Bang? Evidence 1, the expanding universe. In 1929, Edwin Hubble observed that distant galaxies are moving away from us, and the further away they are, the faster they are receding, every direction. every galaxy, all moving away. This is Hubble's law. And it has one inevitable implication. If you run time backwards, everything was once closer together. Wind the clock back far enough, and all the matter in the observable universe was compressed into an extraordinarily small region. The expansion of the universe is not an inference or a model, it is a direct observation, measured in the redshift of galaxy spectra, confirmed by thousands of independent observations. Evidence 2, the cosmic microwave background. In 1965, American radio engineers Arno Penzias and Robert Wilson were trying to eliminate annoying background noise from a sensitive radio antenna. They cleaned it, checked it, even evicted pigeons that were nesting in it. The noise remained. It was coming from every direction in the sky, uniformly, at a temperature of about 2.7 Kelvin above absolute zero. What they had accidentally discovered was the afterglow of the Big Bang itself. In the early universe, matter and radiation were so hot and dense that the universe was opaque. Light could not travel freely. About 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with protons forming neutral hydrogen. The universe became transparent, and the light that had been trapped streamed freely in all directions. That light, stretched and cooled over 13.8 billion years of cosmic expansion, is the cosmic microwave background, the CMB, the oldest light in the universe. And here is something genuinely worth being proud of. Australian radio telescopes, including CSIRO's Parkes Observatory in New South Wales, affectionately known as the Dish, have contributed to cosmic microwave background research and large-scale structure surveys of the universe. The Dish that helped receive the first moon landing transmissions in 1969 also helped map the universe. Evidence 3, the abundance of light elements. Big Bang nucleosynthesis, the theory of how hydrogen, helium, and lithium were forged in the first 3 minutes after the Big Bang, predicts precise ratios of these elements in the universe, about 75% hydrogen and 25% helium by mass. Observations of ancient stars and gas clouds, formed before any later stellar processing, match these predictions with extraordinary precision. 3 independent lines of evidence, 3 completely different physical phenomena, all pointing to the same conclusion. The universe was once extraordinarily hot and dense. It has been expanding and cooling ever since. That is not a Furphy. That part is rock solid. Now, here is where the story gets genuinely fascinating, and where honest physics must draw a line between what is established and what is theoretical. The standard Big Bang model, as powerful as it is, has some puzzles it cannot explain on its own. Puzzle 1. The horizon problem. The cosmic microwave background is extraordinarily uniform. The temperature is the same. It's a 1 part in 100,000 hour in every direction we look, including opposite directions in the sky that are so far apart they could never have been in contact with each other in the time available. How did regions of the universe that were never causally connected, that could never have exchanged information or energy, end up at exactly the same temperature? Puzzle 2. The flatness problem. The geometry of the universe is extraordinarily flat, meaning the total energy density is almost exactly equal to the critical density. The probability of this happening by chance, in standard Big Bang cosmology, is vanishingly small. In 1980, American physicist Alan Guth proposed a solution to both puzzles, and it is extraordinary: cosmic inflation. In the first tiny fraction of a second after the Big Bang, far shorter than any time you can meaningfully imagine, the universe underwent a period of exponential expansion. Not just fast, exponential. Space doubled, then doubled again, billions of times, in a time interval of roughly 10 to the power of negative 32 seconds. In that extraordinary moment, a region of space smaller than a proton expanded to a size larger than the observable universe today. The horizon problem is solved, because the entire observable universe was once a tiny region in causal contact. It reached thermal equilibrium, then inflation stretched it to cosmic scales. The uniformity is a relic of that early equilibrium. The flatness problem is solved because inflation stretches any initial curvature flat, just as the surface of a balloon looks flat when inflated enormously, even if it started curved. Now, here is where Feynman's honesty is essential. Inflation is extraordinarily compelling. It solves real problems, it makes predictions, including specific patterns in the cosmic microwave background that have been confirmed observationally. But inflation is not as solidly established as the basic Big Bang. We do not know what drove inflation. The hypothetical field called the inflaton has never been directly detected. We do not know precisely when inflation started or stopped, and there are competing models. The basic Big Bang, rock-solid evidence. Inflation, extraordinarily well motivated but still theoretical frontier. That distinction matters, and honest physics always makes it. Now, the question everyone asks, and the one that deserves the most honest answer. What happened before the Big Bang? Feynman would give you a very specific kind of answer to this question, not a dismissive one, not a religious one, a physically precise one. The question, what happened before the Big Bang, may be malformed. Here is why. General relativity tells us that time is not a fixed backdrop against which events happen. Time is part of the fabric of space-time, and at the Big Bang, space-time itself began. If time began at the Big Bang, then asking what happened before, it is like asking what is south of the South Pole. South of the South Pole is not a place. You cannot go further south than south. The question sounds grammatically correct, but it has no physical meaning. Similarly, before the Big Bang may simply not be a meaningful concept, not because we do not know the answer, but because the question assumes a framework, time existing before the Big Bang, that physics does not support. In 1983, Stephen Hawking and James Hartley proposed something called the no-boundary proposal. Using quantum cosmology, they described the origin of the universe as a quantum event with no definite beginning. Time near the Big Bang becomes imaginary in the mathematical sense and then smoothly rounds off, like the South Pole. No edge, no boundary, no before. It is extraordinarily elegant and extraordinarily difficult to test. What we can say honestly is this. The observable universe has a beginning, a moment before which our current physics cannot reach, approximately 13.8 billion years ago. Whether something existed before that moment, in what sense, and describable by what physics, we genuinely do not know. And in that honest admission, there is more integrity than in any confident-sounding answer that pretends otherwise. Here is the idea that Feynman, and with his deep roots in quantum mechanics, would find most compelling about the origin of the universe. At the Planck scale, the smallest meaningful scale in physics, about 10 to the power of negative 35 meters, quantum mechanics dominates everything. Space, time, energy, all governed by quantum uncertainty. At the moment of the Big Bang, the entire observable universe was compressed to scales approaching the Planck length. This means the origin of the universe is fundamentally a quantum event, and quantum mechanics, as we know, is deeply strange. In quantum mechanics, events do not have definite causes in the classical sense. Virtual particles pop into existence from the quantum vacuum, without any prior cause, borrowing energy from uncertainty. Some persist, some annihilate. Some physicists, including Hawking, Alexander Vilenkin, and Lawrence Krauss, have proposed that the universe itself originated as a quantum fluctuation, a spontaneous appearance from a quantum vacuum state. Not from nothing in the philosophical sense, from a quantum vacuum which is emphatically not nothing. It is a seething, energetic, quantum mechanical state filled with virtual possibilities. Think about it this way. The quantum vacuum is like Bondi Beach at 6 a.m. It looks still, quiet, empty. But underneath, the ocean is constantly moving. Waves forming and dissolving, energy transferring. Nothing is truly static. From that quantum ocean, under the right conditions, a wave can grow, amplify, sustain itself. The universe may be that wave. A quantum fluctuation that found a way, through inflation, to become self-sustaining, to expand, to cool, to generate the complexity of stars and galaxies, and eventually, curious minds asking where it all came from. Is this certain? No, it is frontier physics. Is it compelling? Extraordinarily. Does it remove the need for a creator? That is a philosophical and personal question that physics does not answer, and Feynman would be the first to say so. Physics describes how. The question of why, in the ultimate sense, remains open, as it always has. If we are going to talk about the beginning of the universe honestly, we should also talk about its end, because the physics of the end is just as extraordinary as the physics of the beginning. The universe is not just expanding, it is accelerating. As we covered in our Einstein field equations video, dark energy is driving the expansion of space faster and faster. If dark energy remains constant, and current observations suggest it does, the universe faces a fate called the Big Freeze, also known as heat death. Over trillions upon trillions of years, galaxies will drift apart, stars will burn out, black holes will evaporate via Hawking radiation. The universe will approach a state of maximum entropy, uniform, cold, dark, and essentially inert, not with a bang, with an extraordinarily long, quiet thermodynamic sigh. Some models predict a big rip if dark energy grows stronger over time, where space expands so fast that galaxies, then solar systems, then atoms, then space-time itself is torn apart. Others predict a big crunch if the universe's expansion eventually reverses, compressing everything back to a singularity. Current evidence favors the Big Freeze, but our understanding of dark energy is still incomplete. Here is a thought that puts it in perspective. The sun has about 5 billion years of fuel left. After that, it will expand into a red giant, probably engulfing Earth, and eventually collapse into a white dwarf. By the time the last black holes evaporate via Hawking radiation, the universe will be 10 to the power of 100 years old, a number so large it makes the current age of the universe, 13.8 billion years, look like the first microsecond of a very long day. The universe began in extraordinary heat and density. It will end in extraordinary cold and emptiness. And in between, for a cosmically brief window, there is us, asking questions. Let me give you Feynman's honest verdict on cosmology. Because this is the framework that separates good science from speculation, what we know with high confidence, the universe is approximately 13.8 billion years old. It has been expanding since a hot, dense initial state. The cosmic microwave background is the direct observational evidence of that early state. The abundance of hydrogen and helium matches Big Bang nucleosynthesis predictions. The large-scale structure of the universe, the cosmic web of galaxies and voids, is consistent with the standard cosmological model. This is established, evidence-based, peer-reviewed, confirmed by multiple independent methods. What we know with reasonable but not complete confidence, cosmic inflation likely occurred. Dark energy is real and is accelerating the expansion. The universe is geometrically flat to high precision. These are well supported by evidence, but involve model-dependent interpretation. What we do not know, what drove inflation, what dark energy fundamentally is, what happened at and before the Planck epoch, whether the universe is infinite or finite, whether there are other universes, a multiverse. These are genuine open questions, actively researched, hotly debated, honestly uncertain. The Big Bang is not a Furphy in the sense of being false. The core of it, the hot, dense initial state, the expansion, the CMB, is as well established as any result in science. But the popular picture of it, the explosion, the something from nothing, the confident story told as though every detail is settled, that is the Furphy. The honest story is more uncertain, more complex, more surprising, and in Feynman's view, more interesting, because the questions that remain open are the most extraordinary questions ever asked by any creature in the history of this universe. Where did space come from? Where did time come from? Why is there something rather than nothing? Physics is working on it. We are not there yet, and that is not a failure. That is the frontier. So let us bring it all together. Feynman style. The Big Bang is not an explosion. It is an expansion of space itself, everywhere simultaneously, from an extraordinarily hot, dense initial state. No center, no edge, no point of origin in space. The evidence, Hubble's expanding universe, the cosmic microwave background, and Big Bang nucleosynthesis, is rock solid, among the most well-confirmed results in all of science. Cosmic inflation, the extraordinary period of exponential expansion in the first fraction of a second, likely explains the uniformity and flatness of the universe. Well motivated, partially confirmed, still frontier science. What happened before the Big Bang may be a malformed question. Time itself began at or near the Big Bang, the Hawking-Hartle. No boundary proposal suggests the universe had no definite beginning. just as the South Pole has no south. The quantum origin of the universe, a spontaneous emergence from the quantum vacuum, is compelling and genuinely possible, but not yet confirmed, and the fate of the universe, the big freeze, is the most likely ending. Trillions of years of cooling, darkening, and quiet thermodynamic inevitability. The universe began in a whisper of quantum probability. It will end in the silence of maximum entropy. And in between, there is physics, there is curiosity, there is Curious Physics AU. If this video rewired how you think about the universe, smash that subscribe button and join the Curious Physics AU family. New videos every week, built for Australian students and anyone who wants the honest story of the cosmos. Drop a comment below. What surprised you most? The Big Bang not being an explosion, the no boundary proposal, the quantum origin of the universe? Tell me what landed. Share this with someone who confidently explains the Big Bang as a massive explosion, and watch their mind get gently, thoroughly, lovingly rewired. For the HSC and VCE students, this video is your deep background for cosmology, the expanding universe, and the origin of space-time. The questions here connect directly to your study of modern physics. I will catch you in the next one.